Good evening, everybody. Thank you for coming tonight. Welcome to Turfgrass Epistemology. My name is Travis Shaddix. I hope everybody's doing well. It is January 10th, Wednesday evening. Fairly miserable day today in Lexington. Very gray and windy and wet and cold. And we're going to have a nice day tomorrow, and then it's going to turn bad again on Friday, and then we should be in the clear, I hope. We're not getting it near as bad as some of the Northeast, so I hope everybody up in the Northeast is doing well. I don't know if anybody's out of power up there, but I saw a lot of damage, and it's unfortunate. So I hope everybody's staying safe and warm, and it's just one of those times, a freak storm. I think we caught like the south end of it yesterday or last night and today, and then there's a break, and then as it comes down, we're catching the back end of it tomorrow. So, hopefully it all goes well. I haven't seen or heard of any or harm to anybody in Lexington. I know there's been some damage, but not anybody's been hurt as far as I know, but I could be wrong. Anyway, thank you all for being here. Super TA, Mitch Bird. It's cold and nasty in Dayton, Ohio. Yeah, it's not much nicer here. Yeah, Looney, we're doing the soil pH diagram today. Oh, Ulysses says that. Oh, I did this is the second video or second podcast for today. I'm actually doing 2 on Wednesdays now. And the one this morning, I went over a video of a gentleman. I can't remember his name. Well, maybe you have his name in here. I can't remember his name. Anyway, he was unfortunately fooled by a product that had a lot of iron in it, and he bought and applied the product because there was a lot of iron in it. And Ulysses says he just watched this morning's show, and the Protein 600, which was the product he was putting out. The guy appeared on the Grass Factory and is a good friend of those guys. Okay, good deal. And he sells that product. Well, if he sells the product, then, we can have a different conversation. I actually was feeling sorry for him because to me, he seems like a innocent victim of the iron propaganda, on granular fertilizers for turf grass. We just don't see a whole lot of a response, particularly from iron humate. And there's quite a bit of evidence to support that statement. And, he seems like a nice guy. Nothing against him. I was just more showing that as an example of how people can be easily fooled by information. And he actually did the right thing. He was skeptical and looked into it. Unfortunately, he went to the wrong source. He went to the person selling it to get information, and they're very rarely truthful. I once was when I was working for a fertilizer company, I was once at a national meeting, and we had just released 2 products. One product was labeled I'll leave the names out of it, but it was labeled as they were wetting agents. And one product was a moisture penetrant or soil penetrant. And that was one product. And the other product was a retainer. So we had one product sold as a penetrant, and that was the marketing scam behind it. And one was marketed as a retainer, meaning it would retain moisture in the upper surface as opposed to the other product pushing moisture through. I knew it was a scam from the beginning. And I was at a national meeting not the business meeting, at a association meeting. And the customers were coming up to the product developer of the company I was working for. And were asking him questions about these 2 products. And I knew they were nonsense. I mean, I knew both of them worked as wetting agents, but there's no evidence to say one is a penetrant and one is a retainer. That's silly. And they were asking him questions. I was listening to give the responses, and I was just thinking, you're completely full of it. I mean, what are you saying? And one guy asked him, is it possible to mix them together and have it retain it for a short period and then penetrate the soil afterwards? And he goes, yeah. I was like, what are you doing? So the guy left, and I pulled the guy over to the side. I was like, what do you say? Why do you say that? You don't know that's true. And he goes, well, he doesn't know it's true either. I'm like, are you kidding me? So, I mean, It's just stuff like that happens in businesses all the time. And when it comes to iron, I generally think the majority of people just don't know. Even the manufacturers and distributors, most of them don't know. But if they do know, they know it doesn't work. There's no one that will tell you with any, well, they might tell you, but there's no one who can say for sure that, yes, that granular iron is going to result in a turf response, because there's almost no evidence to support that. And so that's what I was going over this morning, that he called the wrong guys, unfortunately. And of course, they're going to say that works. Of course, they're going to say it's plant available. By the way, soil scientists almost never use the phrase available. It's usually soluble or extractable or something along those lines. We can't say as a soil scientist, just because something's soluble, I can't say that it's plant available. Okay. It doesn't always work that way. It has to be soluble to be plant available, but just because it is soluble doesn't necessarily mean that it's plant available. So we generally don't use that phrase. So when you hear someone say, if you ask, is this soluble, or will this fertilizer, will it result in a response, or will it be available? And the person says, yes, that when you put it in the soil, it will be plant available. I think some of that's just marketing and just salesmanship. But if it comes from someone who's claiming to know what they're talking about, I can assure you they probably don't if they use that phrase. We just generally don't, we don't use that language in general, because I can't say that it's plant available. I can only say that it's soluble or insoluble. I don't know for sure that it's actually going to be plant available just because it's soluble. Anyway, let's see. Today, I was going to show a video. We're going to go over. I was going to go over the last of one of my topics of the article, or one of my articles on the topic of iron and manganese. I'm going to go over that on Monday. I actually had it listed earlier, and I changed the title of this podcast at the last minute because I wanted to go over this soil pH diagram. And we all know what I'm talking about. I'm going to show you just in case you don't. For those new listeners or viewers who might not know what I'm talking about, don't worry. I'll fill you all in on it. But I wanted to go over it. And so today I'm going to go over the basic introduction and a summary of the diagram. And so this will be a part 2 series. This will be part 1. And then next Wednesday night, I'll go over the part 2, which is really the nutrient dynamics between soil pH and nutrients. Tonight's going to be, how did we even come up with this diagram? Well, how did it even get into the lexicon of our turf industry? Why does it still exist? And what are some of the basic limitations of it? And then next Wednesday night, I'll go over in much more detail the sister paper of this. Well, not really sister paper. It's not part 1 and part 2. They stand independently of each other, but the more detailed version from the same authors of this paper tonight. I'll go over that one next Wednesday night. And then that'll cover the 2 pH diagram papers I wanted to cover. And then I'll go over iron, 2 or 3 more papers next Monday, Tuesday, Wednesday. And then for the most part, that'll wrap up iron. I might do another week on iron with some plant stuff or something. But that's that's the plan. And don't forget, tomorrow night, I'm on the Grass Factor at 9. And at the end of today, you all will impress the hell out of me if anybody knows where this music comes from at the end of the show tonight. Okay. And I don't mean just Shazam or just, YouTube. You can find it. I mean, it's on there. But this song will come from, well, how should I say this? Yeah, I'll say it because you probably won't know it anyway. Not that it matters. Even if I say kind of the genre, can't imagine anybody's going to know where it comes from. But it comes from, in my opinion, the greatest console video game of all time. But it's like the hard rock version. The redo of the soundtrack in heavy metal, basically. So that'll be at the end. I used to listen to that, believe it or not, back in I guess it was early, mid 2000s, I guess it was. I burned it onto a CD and I listened to this song. And this is not the exact version of it, but I couldn't find my CD. I went through my whole CD collection downstairs and I couldn't find the dang thing. So I had to settle for the one I have on tonight. So anyway, welcome on everybody. Jeremy Bosch, Chad, Mitch, Corey. I'm not sure if I recognize that handle, but welcome. It says Northern Virginia. I guess that's where you're from, Northern Virginia. Welcome. Gray. Turf Nerd Lawn Care. Brady, Gardner Earth, very familiar names. I'm glad I got a little bit of a regular audience. Is anybody else besides myself getting a little bit excited when you hear the intro music starting? You're like, okay, yeah, now it's starting. You kind of get your heartbeat. You know, I get a little excited now when I hear that. It's starting to kind of connect with me at a different level. Like I hear that music and I know I'm about to get started. I'm starting to get a little excited when I hear that music going at the beginning. But I don't know, maybe it annoys you guys. I don't know, but I kind of, I'm getting a good feeling every time I hear it now. So maybe it's starting to kind of wear on me a little bit in a good way. All right, let's get started. I think what I'm going to do is I'm going to start off this topic by, I was going to show a video, but honestly, there's probably 50 different videos with this pH diagram in it. And instead of going through a YouTuber, I thought I would actually show it in, I think, a little bit more meaningful or impactful way. That they introduce it in a more impactful way, meaning it's not just in YouTube. I'm going to show it actually from a university. The pH diagram is actually oftentimes used in university publications. In fact, hang on one second. In fact, I think it's in this. Let me see if it's in here first before I show it. I'm almost certain that it is. I'm looking at the old Florida BMP. Yeah, it is right here. The old Florida BMP. This is the best management practices for enhancement of environmental quality on Florida golf courses. So this is what I'm looking at here. For those watching, they can see it on the screen. This is an older version. There's 4 or 5 iterations of this. This is from 2007. And in here, in chapter 5, you'll see a diagram that looks like this. You'll all be very familiar with this diagram, I'm sure, if it gets into focus. There you go. And it shows a series of colored bars. It's a graph that has pH on the x-axis and a variety of different elements, nitrogen and phosphorus and potassium and so forth. So this is in the old Florida Golf Manual. When we redid this in 2018, I wrote those chapters and I pulled it out. So it's not in the new one for a very good reason. I removed it, and it's not in the Kentucky BMP manual either. You'll understand exactly why I took it out over from today and next Wednesday. You'll understand my opinion and understand why I had a good reason to remove it. It didn't have any business being in there to begin with, but not just in Florida. It's also in other places as well. So this one, I'm looking at the NC State extension. I'm going to pick a little bit on NC State, but don't worry, Virginia Tech. I'm going to pick on Virginia Tech in about 5 minutes. So I'm an equal opportunity offender, I suppose. So and this is the North Carolina Extension Gardener Handbook. And you can probably find this at 15, 20 different university handbooks, honestly. It's bled its way into our normal conversations on soil and plant nutrition, unfortunately. But I just want to point out that it's not just YouTubers saying this. They get this from stuff like this. So if you go through here, this is actually a book, but to get the book, you have to buy it. I don't think you can download the PDF or anything. But online, you can see all the content from the North Carolina Extension Gardener Handbook. And if you go down here, you'll see some diagrams and figures and pictures and all sorts of stuff from gardening and all, various things related to gardening and nutrition and so forth. And here you'll see the diagram. And for those listening, it's a similar diagram as what's in the Florida document. And it shows pH on the x-axis, and it goes from 4 to 10 on pH. And it shows the various elements, nitrogen, phosphorus, potassium, sulfur, down to molybdenum, copper, and zinc, and boron, all these things. And it shows that it had different scales. It goes from a very thin, the idea is the thickness of the bar. It gives it a relative, visually depicts its relative solubility. So the thinner the bar, the lower soluble that particular element would be at that pH, or the less soluble it would be. So for example, phosphorus is very, insoluble down towards the lower pH range, and then it goes up around 6 and it stays soluble around 7 and so forth, and it goes back down and then comes back up at 8.5 and so forth. Iron is very soluble down the low pH ranges, and then it declines, but it shows some solubility out to 9 and 10, which is completely absurd. So manganese is the same way. There's also, it just gives you an idea of what I'm talking about. This is the diagram I'm talking about. For those of you who might not have been familiar, the concept or the idea behind it is to give people a visual indication of the importance of pH and how it influences the solubility of nutrients in the soil. Okay? And I'm telling you right now, stop using it. It's horrible. It is not useful for anything other than the basic concept that nutrient solubility changes based upon pH. It has very little usefulness when it comes to the actual uptake of nutrients by the plant at a given pH. There are at least 3 elements on this graph, as we will learn. I think it's going to be next Wednesday. As we will learn, there are at least 3 elements, macronutrients, on this graph whose plant uptake increases as the solubility decreases. And the uptake decreases as the solubility increases. Nowhere on this figure or this diagram is there any indication or any consideration at all of the influence of the plant itself or the interaction with other elements with a given element. So, for example, interaction of, phosphorus, or the interaction of aluminum with plant uptake. Forget the phosphorus, just the toxicity of aluminum alone at a low pH. Or the uptake of calcium would be influenced. And the idea would be like you would apply calcium at low pHs, and that would increase plant growth because you're applying calcium, but it's not necessarily because of that. It's oftentimes because you're alleviating a toxicity of another element. So there's all sorts of stuff going on here that do not coincide or they conflict with this diagram. So I've been saying it for a long time, and I love my old colleagues at UF, but when I was telling them this, to take this out of the BMP manual, they're like, well, this has been in there for years, I was like, I don't care if it's been in there for 150,000 years. I don't care if it's not valid. It's not useful. We need to take it out. It's not a BMP. And I'm going to build a case. Actually, the authors of this paper today and the authors of next Wednesday are going to build the case. I'm just going to communicate it. But I agree with them completely. In fact, there was a tweet sent out by Dr. Doug Soldot maybe 6 months ago or a year ago, promoting this publication that I'm going to talk about today. Okay. He was promoting it and saying, hey, there's a publication out about the pH diagram. And I replied back to his tweet. In fact, I probably should have queued that up and had it ready to go. And I replied back to his tweet saying, I agree. And I had a little video clip of me talking about that diagram like a year or two prior, telling people to stop using it. It's horrible. Okay. And I don't, and this is one case. What I would like to say is, when you're seeing salesmen use it, they're BS artists. They're trying to BS you into buying something. I would like to say that. But in this particular case, I don't think I can completely say that because it is so ingrained in our thought process of soil fertility and turfgrass science that they probably genuinely believe that what they're saying is true. I don't know if they're intentionally trying to deceive anybody. They probably actually believe this is true because right here it is in a university publication, NC State and Florida. Well, no longer Florida, but it was in Florida's. It's in university stuff. It's on YouTube all over the place. It's on gardening websites all over the place. So when you hear someone talking about it, what I think initially is they don't know what they're talking about. But I empathize with them because they probably are just victims of decades and decades and decades of misinformation and misunderstanding what this diagram actually does and how it can be used. So that's what I'm talking about. That's the sort of the introduction of tonight, is that we're going to be talking about this diagram. But the question I have before I even go into the details of this, which will be next Wednesday, is how we even got here. How did they even get to this point? You're saying, okay, Travis, you're just saying all this stuff. And you're right. This is all I'm telling you right now is just my opinion. You don't know what my opinion's based on. I haven't shown you that yet. I'm just saying it. So if you're saying, well, I get it, you don't like it, but why are you convinced it doesn't work? That's what we're going to get into, okay? Or why are you convinced that it's not useful, I should say. So what I want to do first is go to the very first known publication that contained this document, and that was in 1935 in a publication from Virginia Tech. So Virginia Tech, I told you I was going to pick on you a little bit. And that's where it came from. It came from a guy named, what was his name? Pettinger. This document can be downloaded for free. Just Google it. It'll pop right up. It's called Bulletin Number 136, a useful chart for teaching the relationship of soil reaction to the availability of plant nutrients to crops. March 1935. It's a fairly long document. It's fairly robust. You can go through there and it talks all about soil reaction and acidity and all these things. I think his name was Nicholas Pettinger. At the time, it was called Virginia Agricultural Experiment Station, but this is Virginia Tech nowadays. You can go through here and read all you want to read, but I'm going to scroll down quite a ways. It talks about acidity and neutrality and alkalinity and all these things. When we get down here, this is the first known diagram of this concept. And to be frank, I would have thought you made this diagram last week. This thing was made 90 years ago. It looks pretty good for a publication that was 90 years old. I mean, done 1935. You have to remember, Hitler just took over in 1933. He's the chancellor of Germany at this point. He's a dictator at this point. We're coming out of the Great Depression. Well, not yet. We're still in the Great Depression. We're trying to get out of the Great Depression in 1935. There's a lot of stuff going on in the world, just chaos, that's about to ensue in about 5 years. 4 years, actually. And they're making these little diagrams, in 1935 extension bulletins. And I think it looks pretty good. If I could remake this today, I'd be happy with myself. And they did that back then. Well, what I like about this down at the bottom, it says a larger lecture size, 3 feet by, what is that? 6 feet of this same chart. So a 3 by 6 foot chart, or what is it? I don't even know what that is. 3 by 6 feet chart on 80-pound offset paper may be obtained by writing the Office of Publication in Blacksburg, Virginia. And you can write that and enclose $1 to cover cost of printing and mailing. $1. Back then, that $1 was a lot of money. So you could have bought this for $1 for a 3 by 6 chart. I wonder if they still accept that. I wonder if I sent something there to them right now, if they'd send me a 3 by 6 poster of this chart. So this is the first known chart. All right, 1935. Well, the article I'm going to talk about actually describes all of this. But let me show you the next, it didn't do anything for about 10 or 12 years. Nothing really happened. And then another guy came along, Truog. Now, Emil Truog was the same guy who invented the Truog soil extraction for phosphorus. He was very well known, very, very well established as a soil scientist. And he took that chart from the 1935 Virginia Tech, and he amended it and kind of adjusted it into what is more common today. We kind of see this now today. He added a few elements. He removed a couple elements and renamed them. And this looks a little bit more familiar with what you probably are familiar with today. Okay. So from 35 to 47 or 46, nothing really happened. And then this came along. And then from here, things started to build. Okay. So let's go into the article today. The article today was just published this year, or 2023, last year. It's called Soil pH Nutrient Relationships, the Diagram, by Alfred Hartemink and Barrow. Now, in the world of turfgrass science, there's one or two people who are at the very pinnacle of their potential, and coincidentally, at the pinnacle of turfgrass science in the United States. One of them is Dr. Richardson at Arkansas. If you look him up on Google Scholar, in fact, someone can do that right now and do me a favor and just do that and post it in chat. Look him up on Google Scholar and look and see what his number is on Google Scholar in terms of citations. I want to say it's in the 5,000s, 5 or 6,000, something like that. Very, very high. I don't know of another turf scientist who has a higher citation number than Mike Richardson. And I'm sure I'm wrong. Maybe Beth does, or who knows, maybe there is somebody, but Mike Richardson is very, 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 very high up on the scale. That's about as high as you're going to get in turfgrass science, 5,000, 6,000 citations. This author right here, look him up. Go on Google Scholar and look him up. Alfred Hartemink, he's at Wisconsin, I believe, has 12,000 citations or higher. For an agriculturalist, for an agronomist, that is insane. Okay, it's absolutely off the chart insane. Okay, so I'm just saying that to say this. These are not assistant professors trying to get their name on some ink and, get tenure. These are extremely well-respected, well-established, well-published authors who are going to talk about this. And these are the same two authors that we're going to talk about next Wednesday night. Okay? These guys, and like I said, the most published turf professor scientist in the United States that I'm aware of has less than half the citations of Alfred. So, and I'm not putting Dr. Richardson down. I mean, he's the best published one I know of. He's up there at the top. And this guy has doubled him, Alfred Hartemink. So this isn't a fiddle-faddly sort of playing around art document. This is a very well written, well established author, well written paper, and we're going to go over it. Okay. This was published in Plant Science in 2023. So just this year, and I don't believe it's for free. I believe you have to be a member or pay for it. Okay. Published online January 4th of 2023. I'm probably going to end up having to read most of this. It's not that long. You can see it's only 4 or 5 pages. It's not very long at all. But I'm probably going to read most of this because I really want to set the stage, because next Wednesday night's paper is much more complex. But I want everybody to understand why it is we even look at this. How did it even get here? And then understand some basic limitations and basic usefulness of the diagram before we go in deeper next week. Let's see. So the introduction. Acid soils occupy approximately 30% of the terrestrial Earth and are found in humid and subhumid regions. Northern regions that are dominated by cold and temperate climates have acidic soils that are classified as spotosols, alphasols and acetosols and histosols. So these are all soil classification terminology. When you all hear this, it just sounds maybe like Greek, but when a soil scientist hears this, they know that this first four letters and the last 4 letters mean something to me. I know that a spotosol, it has this sort of criteria, it has this sort of delineation in the soil, an alphasol, and a histosol, and so forth. And ultisol and oxasols, all these are very, it's very specific language for a soil scientist, so we understand what they're talking about. I don't know if that matters to you all or not, but whatever. Alkaline soils occur in the western U.S., large areas of Argentina, North Africa, and the Middle East, and extensive areas in China and Australia. At a global level, there is a pattern between the soil pH and the climate whereby soils with high pH are common in arid regions, and acidic soils are common in many humid and subhumid regions. Small changes in water balance cause a steep transition from alkaline to acidic soils across climate gradients of the globe. Other factors that affect the soil pH include soil parent material, which largely determines mineralogy and soil texture. However, there are also some exceptions to this relationship, such as high pH soils in tropical lowlands and in poorly drained soils. So he's going to basically, they just go through and explain sort of the global, picture of what's going on with soils and the general partitioning or general areas that these soils are found. Okay. Soil acidity and soil alkalinity in relation to plant growth has been well studied. The soil pH is often used as an indicator of the chemical fertility of the soil and it is believed that most major and minor plant nutrients are best available around a slightly acidic pH. This concept of soil pH nutrient availability, the Achilles heel of soil fertility studies, was first developed in 1930 and 1940s based on field trials, observations, and various assumptions. 1930 was the first paper I just showed you. The 1940s was the Truog paper that I just showed you. A soil pH nutrient availability diagram was developed for the humid regions of the United States that showed the availability of some major and minor nutrients at a pH range from 4 to 10, which is what I just showed you on the Petting, or what was, I always forget his name. Nicholas Pettinger right here. Okay. Nicholas Pettinger. It became known as the Truog diagram because Pettinger made the diagram and then Truog kind of fine-tuned it and then promoted it kind of. It's kind of like the difference between Furman Bear and the guy at Missouri that did the base cation saturation. I can't remember his name now. But anyway, it's known for him, but really Furman Bear was the one who started base saturation, which I'll get into, by the way. By the way, this diagram is sort of like the pH version of the base cation saturation. Base cation saturation is completely useless. And this diagram is basically completely useless, but they're so well established sometimes in people's minds that it's mind blowing to get them to think that doesn't work. It's just an earth shattering moment for them in their mind. They have to, it's going to take a long time to convince people who are already so well convinced that this is working. It's going to take a long time to convince them that no, that's not the way it works. Okay, so I empathize for sure. So it became known as the Truog diagram, and it has guided soil fertility research and has been widely reproduced in scientific and popular textbooks. That's what I just showed. I just showed you the UF, or the Florida textbook, or the BMP. I just showed you one from North Carolina State. You'll see them all over the place. This paper reviews the history and origin of the diagram, including its limitations. Okay. So I'm not going to go into the whole Emil Truog history and stuff, but I mean, just real briefly, Emil Truog was born in 1884 on a farm in the driftless areas of Wisconsin. Goes through all the stuff, his history and how he came about and how he grew up and how he became well versed in soil fertility and soil chemistry. And there's no question he was. I mean, absolutely. He was very well known at the time for being an authority in this area. I'm not going to, if you want to know more about Emil Truog, you can read through this. This whole first 2 or 3 paragraphs talks about him and his life. Okay. So on a more practical level, he aimed to develop a soil pH test that could be an indicator for how much lime should be applied. He called an acid soil chronically sick, and lime was the cure. A litmus paper test for soil acidity was developed, whereby moist filter paper collected hydrogen sulfide liberated from the boiling soil suspension. So he went through and was trying to work on soil pH tests and ways to, help farmers probably. And then he goes through all this stuff. Okay. The relationships between soil pH, nutrient availability, and plant growth of plants was a prime scientific interest to Truog, which, I mean, I could make that statement. Hopefully that's a prime interest to most soil scientists. I mean, soil pH, nutrient availability, and growth of plants. It's very important. We want to know more about it. And so did he. Although liming of acid soils has been practiced for thousands of years, the scientific basis was not well understood, and particularly the relationship between lime and plant growth. He disliked the view that plants were being lime-loving, lime-avoiding, or indifferent, or likewise acid-intolerant, acid-tolerant, or indifferent. It was also realized that soil acidity has numerous direct and indirect influence on soil fertility, as it affects the physical, chemical, and biological properties of the soil. I mean, if I was to say I'm not a soil microbiologist, but if I was to say one thing positive that I could infer sort of tangentially from that diagram, it's that soil pH generally in the 7 to maybe slightly lower than 7 range is generally where the microbiology tend to flourish. I'm not a soil microbiologist. Somebody, if there is one listening and they disagree, feel free. I'll defer to you for sure. But the microbiology seems to be more soundly supported, I guess, by that diagram, as opposed to the nutrient availability and all this other stuff. It's hard for me to imagine the microbiology flourishing at a pH of 3 or 4 or 9 or 10 to the degree where it would, plants would grow sufficiently. But when you're in the middle zone somewhere, I think the microbiology, because it has such a profound impact on all these other things, I think that would be useful for that diagram, or at least useful to you understand if you move things down way out of the top range or up way out of the low range, you're probably going to see greater plant growth. But it might not be due to nutrient availability. It might be due simply to microbial activity being better at those neutral pHs to slightly acidic pHs. But I'm not a soil microbiologist. That's just my take on it. Okay, the pH nutrient diagram. So in 36, Nicholas Pettinger from Virginia Agriculture Experiment Station published a bulletin, which is what I just showed you from 1936. He stated that the effect of the degree of acidity and alkalinity of the availability of plant foods or the relationship between lime and fertilizers is one of the most widely discussed subjects in agriculture, and probably the most discussed even today. Soil reaction was perceived to be one of the pulses which indicates the state of health in the soil. In the bulletin and diagram that came with it, he discussed the range of soil pH in relationship to the availabilities of potassium. We're going to learn potassium is one element that we might not think. We may have an understanding that is contrary to reality with potassium. Nitrates, magnesium might be another one. Just saying. Calcium, phosphate, iron, aluminum, and manganese. A color diagram was presented that composed a series of bands representing the availability of plant nutrients in a relation between ranges of 4 and 10. Okay, so they're just describing it. And here's the actual diagram from the one I just showed you. He pulled this from 1935 and he put it in this paper as a review to let people know. Limitations of the diagram were discussed. It was stated that the diagram was designed to illustrate basic principles in the availability of nutrients in relation to soil reaction and did not portray the situation in a quantitative or absolute manner for any particular soil. The diagram was considered only valid for well-drained soils of humid regions and not for alkali soils or arid regions or poorly drained or organic soils. Now, if you ask 999,000 people who've seen this diagram, if you said, "Hey, is this diagram useful for soils?" They'd say, "Yeah." Not 1.001% would know, probably, that in the original publication, he said, "It is not intended to portray the situation in quantitative or absolute manner of any particular soil. It was not considered. It was considered only valid for well-drained soils of humid regions and not for alkaline." It was a very specific area that it was designed for. It wasn't designed for worldwide soils in any pH in any soil. Okay. He recognized the Pettinger, I guess it was, recognized the availability of some nutrients was directly affected by soil reaction, whereas for other nutrients, the availability was controlled by processes that were not related to the soil reaction. I'm going to repeat that again because it seems vaguely important. The author recognized that the availability of some nutrients was directly affected by soil reaction, whereas for other nutrients, 3 for sure, the availability was controlled by processes that were not related to the soil reaction. So it had nothing to do with the soil pH on some of them. Some of them it did, some of them it didn't. He also reported that some investigations showed a somewhat different trend. Finally, he noted that when the discovery of new evidence makes it necessary to discard present beliefs, either wholly or in part, or when better methods of representing the facts are developed, the diagram will be revised and reissued in improved form, which really hasn't happened. Here it is, but that did not happen. So maybe that's in the back of my mind. I realized they wrote that. But that did not happen. He died at the age of 34, the same year the diagram was published. So the guy who published it died the same year it was published with the intention of saying that, hey, we'll adjust this and make changes to it when there's evidence to support it. Well, he died and nothing really happened. And here we are 95 years later, 90 years later, still dealing with the same nonsense. Okay. The Nicholas Pettinger Bulletin was not widely distributed or recognized, but the bulletin was received by Truog, who by the 1930s had become a national leader in soil fertility. Like I said, he was very well known. In the late 1930s, his work of the availability of plant nutrients emphasized that the availability of plant nutrients was a relative matter and that the availability should not be replaced by readily available and unavailable by difficulty or slowly available. He considered the effect of climate where, I don't know if I want to read all this stuff. It became all right, I'm not going to read all that stuff. Okay. Oh, here, this might be important for my later thing. Also, different cropping systems and crops have different levels of nutrient requirements and sufficiency levels. In addition to the importance of nutrients in the subsoil, the interdependence of factors beside pH was underscored. So I just want to point out, I'm going to come back to this in a month or two. Different cropping systems and crops have different levels of nutrient requirements and sufficiency levels. Not every turf grass has the same demand for nutrients, and the sufficiency level for a given turf grass is very likely to be different for a different turf grass. You can't use one sufficiency level for every turf grass. Okay. Despite a nuanced and expanding view on nutrient availability, Truog liked the soil pH nutrient availability diagram of Nicholas Pettinger and considered it very useful and the subject of tremendous importance in connecting with liming, fertilizing, and soil management. He expanded the diagram to 11 nutrients and made it more simple, so he made adjustments to it. The diagram illustrated the relationship of the soil pH to plant nutrients, in which the width of the band at any pH value indicates the relative availability of nutrients. The band did not present the actual amount, as that was affected by other factors such as type of crop, soil, and fertilization. For the 11 nutrients on the diagram, a pH of around 6.5 was most favorable, but did not mean a satisfactory supply. It indicated that as far as the soil reaction was concerned, the conditions were favorable. That's a good way to explain it. As far as the soil pH is concerned, it's favorable. But it doesn't mean it's going to be available for plant uptake. That it doesn't mean iron is going to be available for plant uptake at 6 or 7 or 8. It doesn't mean that. As we've talked about iron for the last 2 or 3 weeks, whatever it's been, I've shown very clearly that even on soils of pH 5.1, 5.3, application of ferrous sulfate immediately becomes insoluble. It doesn't mean it's going to be soluble. It doesn't mean it's going to have enough iron in solution to sustain plant growth just because of the soil pH. Doesn't mean that at all. It just means that soil pH is favorable. Doesn't mean it's going to be available. Likewise, it did not mean that outside the favorable range, a deficiency would prevail. So just because you're in it doesn't mean you're going to be okay, and just because you're outside of it doesn't mean you're going to be not okay. You're going to have problems. It doesn't mean that. It was never intended for that, but people have looked at it that way. Nutrients outside the optimal range could be adequately supplied as other factors other than soil pH affect plant growth, or as some plants had low requirements for a particular nutrient. Like I said, soil pH is important, but when it comes to the solubility of nutrients, that's just one factor of many. Okay? The soil pH, let's just take iron since we've been talking about iron for so many weeks. The soil pH is one factor. The redox potential is another factor. The dissolved oxygen is a third factor. The plant root exudates is a fourth factor. There's just the organic ligands in the soil is a fifth factor. All of those things combined will give you a rough idea of the availability or solubility of the iron in solution for plant uptake. But just looking at the soil pH diagram, well, where's the diagram? Right here is iron. And it shows iron being soluble. Or does it even say available? Yeah, it says soil pH and nutrient availability. It shows it being available clear out here to 10. It's absurd. There's no meaningful amount of iron soluble in soil solution. Let's take all the other factors out of it for a minute. There's no really any meaningful level of soluble iron until you get down way into the 4s. Okay. So this whole idea that, oh, well, iron, that's 7. I got a 6.5. I'm going to have a little bit of iron there. No, you're not. No, you're not. Okay. Sorry. The plant's probably going to be taking up iron through different factors that are not on this chart. Okay. Okay, now let's get into limitations, and we're almost done. Maybe I can finish in an hour tonight. I'll tell you what, if I finish in an hour, and you guys want to make a phone call or something, I'll put the phone number up. You gotta let me know in chat. Somebody can call in if you want to call in. All right, limitations. The soil pH nutrient diagram was presented as conceptual in 1937 and 46 and contained several assumptions. It assumed the availability of nutrients was the same to all plants in all soils, and that it was best to have the soil pH of 6.5. Now, where have we heard this before? It assumes it's the same for all plants in all soils. It's going to be the same for all turf grasses in all soils. That's what this pH diagram assumed. Okay, it's not wise when you start saying all soils and all turf grasses, all plants. However, many acidic soils are highly productive, as are some soils that have an alkaline pH. The diagram suggested that deficiencies of micronutrients did not occur at low pH, and there were no problems with the availability of potassium or sulfur at high pH. There are plants that require a high soil acidity, such as tea, pineapple, blueberries, and cranberries, and others that require a high soil pH. Actually, I said that backwards. Oh, yeah. And others that require high pH. Okay, and others that require. So those blueberries, they require low pH. I thought I read that backwards. There are numerous cases in the availability of plant nutrients that do not match the diagram, and some of them were already highlighted by Truog in 1945 or 46, whenever he wrote that. Let me just make sure we're clear. There are numerous cases in the availability of plant nutrients that do not match that diagram. For example, the toxicity of copper and zinc in acidic soils. Truog published that in 1918. The fact that calcium may not be a limiting factor in acidic soils. Truog published that in 1918, which is not uncommon. You could have just said which is common. And Adcock published that in 2001. So calcium may not be the limiting factor in acidic soils. We're going to talk about that in more detail on next Wednesday night. It was often found that despite the low availability of calcium at low pH, liming had limited effect as calcium was taken up from the subsoil. Other nutrients were limiting, in particular phosphorus, or soil drainage was the problem. Improper crop performance. Okay, let me stop there. Let me finish one more. Improper crop performance with liming is often from the reduction in aluminum toxicity, and that's what I wanted to talk about. And calcium deficiency is not always the major cause of poor growth. So what he's saying is, even at low pH, which is on this diagram right here, calcium, it's showing a reduction in plant availability of calcium as you move from 7 down into the 5s and 4s. So the thought process is, or was, calcium availability is low at those low pHs. So we need to apply calcium because the plant's going to be deficient in calcium. And then when they would apply lime, calcium carbonate, or even calcium sulfate, I believe, if I'm not mistaken, they did it in some studies. They saw, lo and behold, they see a plant response, a growth response from the application of these products. They go, well, it was deficient in calcium. When in reality, it probably wasn't deficient in calcium at all. It was probably being toxic to aluminum. That's what they're saying here in this paragraph. Okay. And that's, by the way, that's one of the major misconceptions or misunderstandings, and in some cases, intentional refusal to acknowledge reality when it comes to base saturation. The idea that you need to apply all this calcium to balance things off, they are convinced that you have to do that. It's absolutely absurd. Okay. I don't know what we got to do to convince these people that what they're saying is an incredible waste of money. But when you're that convinced, it's hard to change your mind. And the idea here was, well, we're applying calcium and we're seeing a response. Clearly it was calcium deficient. No, it was aluminum toxic. Okay, so there's a lot more things going on here. Other exceptions to the diagram, besides just the calcium aluminum issue, other exceptions to the diagram include, for example, manganese toxicity at low soil pH. We talked about manganese toxicity once in a prior paper. Iron toxicity on acid soils. Boron deficiencies in alkaline soils. Sulfur deficiencies on alkaline soils. Some of these exceptions to the pH nutrient availability concept have been explained as simply due to the methodology. Okay. The point is, there are exceptions to that diagram that shouldn't exist. I mean, if the diagram was correct, these exceptions should not exist, but they do exist over and over and over. Okay. For example, I'll just make sure I'm clear here, that we're 100% sure what I'm saying. I'm 100% clear. When he says other exceptions to the diagram include a sulfur deficiency on alkaline soils, what he's saying is that we see sulfur deficiencies on alkaline soils. But up here on this diagram, you shouldn't see sulfur deficiencies on alkaline soils because the sulfur availability is going up as the pH goes up. And the sulfur availability goes down as once you get below 6 or 6.5, the sulfur availability goes down. So ergo, you shouldn't have any sulfur deficiencies once you get up into the high pH range. But they're saying we do. And I agree, we do. So there are numerous examples where if that diagram was correct, these exceptions wouldn't exist. And it's the same thing goes for the idea of the scientific model. The idea of we're not done with the article. I'm going to come, there's a little bit more we got to go over. But when the model of turfgrass, we have a model of turfgrass science. Scientists who publish in refereed turfgrass journals, when we publish, we're contributing to the development of the scientific model of turfgrass science. And our predictions within that model must be correct. When we predict something or we make a hypothesis or we based upon that model, we develop a BMP, it must be true. If we find out later that wasn't true, that wasn't correct, we have to change our model because the reality isn't going to change. The model must be changed. And this model, well, this is actually a diagram. This diagram hasn't been changed, regardless of all the evidence that has since come to light that has shown that this evidence conflicts with the model. The evidence isn't going to change. Our model must change. And that's what the turfgrass science model does. We have a model based upon the entirety of all the known published evidence and literature, and things work within that model. And you go, well, you know what? Let's say, for example, let's just use Einstein, for example. We had a model of physics, of the physics of the universe. And then Einstein comes along and says, nope, we should see that star behind that sun. And all the physicists said, no, our model it won't allow that. And Einstein says, I don't care. It's going to happen. You're going to see that star behind that sun exactly at that spot. And he goes, okay. They go, okay. And if Einstein was right, you'll see that star behind that sun. And if Einstein's model was wrong, then the existing model of physics would have stayed the same. Einstein was right. You saw the star behind the sun. The model of physics had to change because the evidence wasn't going to change. You see what I'm saying? So the new evidence comes in, the model has to change. And that does it in all sorts of scientific disciplines. And in the discipline of soil pH diagrams, it hasn't changed, despite all the evidence coming in showing that it doesn't work. So you can have a diagram like that if you want to, but it has to change to fit all the evidence. We have to be able to adjust it so that all the evidence fits. It's like the model of the globe Earth and the model of the flat Earth. The model of flat Earth doesn't fit. The model of the globe Earth fits everything. Now, it could come out at some point that indeed the Earth is not an oblate spheroid. It could be, that would be earth-shattering to everybody except flat earthers. But if there's evidence so compelling that we realize, you know what, the globe Earth model is not correct, we would have to change the globe Earth model because the evidence isn't going to change. So the same thing here, okay? We have evidence to refute it and the model hasn't changed. All right, when the pH is, okay, so he goes on and talks about some other elements, okay? There are different effects of pH on the phosphorus availability. So he's talking about phosphorus here. I might actually want to start back here a little bit. The availability of phosphorus is often assumed to be problematic in low pH soils where it is said to be fixed by iron and aluminum, or in soils with high pH where phosphorus is precipitated with calcium. Of all the plant nutrients, this is probably the most widely accepted pH availability relationship. And in recent review, it has been termed the classic understanding of the effect of pH on P uptake from soils. So if you've ever heard this, the peak solubility of phosphorus is in that middle range because on the low range, it forms insoluble compounds with aluminum and iron, and that's on the low pH range. On the high pH range, it forms insoluble precipitates with calcium. So that's the general feeling or belief. And then let's see what they say. Barrow recently summed up the problem with this model. It makes wrong predictions. There is very little evidence for the existence of the separate postulate sinks for phosphate, meaning calcium at the high pH range and aluminum and iron at the low pH range. There's very little evidence for the existence of these separate postulate sinks, and it has no facility for explaining other aspects of the behavior of phosphates. There are different effects of pH on the phosphorus availability. When the pH is decreased from 6 to 4, the rate of uptake of phosphate by roots increases. The amount desorbed from soils increases. The amount sorbed by soil often also increases. The first two increase the phosphorus availability. The third effect decreases it. The pH phosphorus availability diagram fails the most fundamental test of science and is difficult to understand why it persists. I'm going to read the same red little paragraph like 5 times. I'm sorry. It's too important. When the pH is decreased from 6 to 4, so you're in the 6s, you're going to say, okay, phosphorus is, I'm good, a 6, 6.5. That's where I want to be. That's where the pH diagram says I should be. The rate of uptake, when you decrease from 6 to 4, the rate of phosphorus uptake by the roots increases. The amount desorbed from the soil increases. And the amount sorbed by the soil often increases. The first two increase the phosphorus availability, the third decreases it. Okay? So we can find it difficult to agree with reality, but that's reality. And it's not going to change. Okay? It's just the way it is. Soil pH is a useful indicator of the soil condition, and it affects numerous soil chemical reactions and processes, but it cannot be used to predict or estimate plant nutrient availability, and different plants respond differently as nutrients interact, which can be synergistic as well as antagonistic. These sentences are so immensely important, guys. I'm reading them slow. Rewind it and listen to it again. Or download this article and read it. Soil pH influences solubility, concentration in soil solution, ionic form, and mobility of most plant nutrients. Soil pH affects the availability of many nutrients by the optimum pH for plant growth, but the optimum pH for plant growth depends on which nutrient is the most limiting. Furthermore, the activity of microbial communities and a range of chemical reactions in the soil are affected by fluctuating pHs, so not stagnant, movement in pH. The bulk pH of the soil, commonly measured in a soil-water ratio, may not reflect the pH in the rhizosphere where nutrients are taken up by plants. So the rhizosphere is that small little area right between the root interface and the soil. Very, very small. And that's where the nutrients are taken up. That's the area of the soil that is influenced primarily by the exudates from the root, whether it's hydrogen or whether it's a phytosideriphore. That's the area where the nutrients are taken up. And it says right here, the bulk pH of the soil may not reflect the pH of the rhizosphere. The bulk pH of the soil might be 7. The pH of the rhizosphere might be 2 or 3. Okay? This pH diagram doesn't account for that. The soil solution pH is relevant for soil and plant biogeochemical processes and better a predictor of crop yields than the soil pH measured in a soil-water mixture. So the soil solution pH versus the soil pH is what they're talking about. So soil solution pH is a better predictor, not the soil pH. The influence of soil pH on bioavailability is indirect at best. And I agree completely. Through the competition with cations for dissolved ligands or surface functional groups, and through breaking down of minerals by the protons, which may enhance the bioavailability of some metals. There is also a direct effect on acidity of plant roots and soil microorganisms, and pH at the root surface interface may differ from that of the bulk soil. Some recent research highlighting the importance of root-induced changes in the rhizosphere pH, or some recent research highlighted the importance of root-induced changes in rhizosphere pH. I have one more sentence here, 2 more sentences, and we're done. Again, you can read through this in detail if you want to. I'm just going to read the highlighted part that I highlighted here. That's redundant, sorry. According to Google Scholar, Truog's paper on the effect of acidity on a soil nutrient availability has 146 citations. But his diagram has many more usages, often without citation, which suggests that it has been accepted as common knowledge. It has become a defining principle in soil fertility and plant nutrition. It's a shame. This is one reason why I am moving very rapidly in the direction of a militant approach to nonsense. We have to protect the scientific model. And I realize now I'm not on the screen here with this paper, but sorry here. This is what I'm reading down here. Sorry guys for those people who are watching. Since the 1950s, a large amount of research work has been done on solubility of nutrients, the biological transformations of nutrients in soils, and the effect of soil pH on adsorption and plant uptake. None of that can possibly be summarized in a simple diagram. The relationship between soil pH and nutrient availability remains of interest, as nutrient availabilities in acid and alkaline soils is unique for each each soil, unique for each soil, crop, and climate region. I'm sorry. Many soils experience land use and climate changes that cause changes in the water balance. Okay, so he goes on. So basically, you need to. There's so much variability, and it's so specific to the crop and the plant and the soil that you're not going to get much out of looking at just one diagram and saying, yes, you should do this. No, you shouldn't do that. You should apply this element. You shouldn't apply that element. It's not the way it's intended. It's not very useful to think of it that way at all. And I agree. Like I said, I was talking about this for years and years. I've been saying this, and some of the people and some of my colleagues who I greatly admire, still friends with, are like, "You sure you want to take that out? You sure you're talking about you know this pH been around forever?" Yeah, I'm pretty sure. I'm pretty sure. And so are all these other scientists. To soil scientists who are familiar with the literature, this isn't surprising. What's surprising is how long it's been around. I mean, how can people continue to perpetuate this myth? You know, it just continues to go and go and go. And that's one reason why, like I said, with certain YouTubers and certain just basic misinformation that kind of comes out, we got to cut that off, because this is a perfect example of how something it becomes common knowledge. It gets into the lexicon of our industry. Before you know it, well, of course, it's just of course the pH diagram is a good thing to use. Everybody knows that. No, it's not a good thing to use. So of course, you should apply nitrogen with iron. Of course, nitrogen is going to take it up and get your lawn double dark green. Got to cut that off. Got to knock that off before it grows too big and before people start to believe it. And it just becomes common knowledge that, yes, of course this happens. No, of course it doesn't happen. Okay? We have to use this evidence in published literature as our guiding light. We have to stay focused on the evidence that's published, not by some marketing sheet because ABC State University did some research. Oh, okay, well, I'll use it then. No. If ABC State University did that research, publish it. Show me what they published in a refereed, reputable turfgrass journal. Send me that publication and I'll read the publication. No problem with that. But just because you put it on a marketing sheet, next thing you know, we're putting out retainers for wetting agents and penetrants for wetting agents, and everybody thinks penetrants are wetting and retainers are. Of course, that happens. Yeah, think it's correct. It's not correct. There's no evidence to support this to say that it is correct. But everybody starts to think it because the marketing sheets got out there, and the BS artists got out there and got ahead of the game, and we're playing catch up. Okay, so you got to knock this stuff off before it grows. Anyway, I digress. Let me look through the chat. Let's see here. Anything from me, guys, before I go? I don't see anything from me. I don't see anything from me in here. I really appreciate everybody showing up. Let's see if I have yeah, I think you guys are just chit chat with each other. That's great. I'm glad you guys are doing that. Tomorrow night, I'll be on with the Grass Factor guys. We're going to be doing something fun. In fact, I'm fairly certain that even they don't know what we're going to do. So it'll be a surprise for them too. I don't mean to spoil it or get them nervous or anything. It's going to be fun. Oh, well, there's Ray right there. Maybe Ray, I don't know if he feels comfortable answering, but I'm not sure if Ray knows what we're going to be doing tomorrow or not, but it'll be fun. Ray says pH is one of the many factors for plant performance. It needs to be looked at as a whole, not the factor. Yeah, I mean, it's just one factor. I mean, yeah, I'm not here to poo-poo pH. And neither were these authors. I mean, they stated many times it's important for these things and so forth. But people look at that diagram and go, I should apply more, sulfur to get my pH down because I need more iron and I need more phosphorus. And we're going to learn next Wednesday night that there are clear cases where the solubility goes up as the pH goes up and the uptake goes down. Very clear cases of this happening with at least 3 nutrients. So next week's going to be a little bit more cumbersome because it's a lot more in depth. I said this was an introduction. This is more of a summary of kind of what we're doing or kind of the diagram. Next week is a little bit with the big, we've got to put our big boy pants on and our thinking caps on next Wednesday night. It's going to be a little more detailed for sure. Okay, guys, I'll be on tomorrow night at 9, and then my show will be back on Monday morning. We'll be going over last 3 or 4 or 5 papers of iron. All right, guys, I appreciate everybody showing up tonight. It was a good show. I really appreciate all y'all's contributing. We're up to 400 and something subscribers now. That's fantastic, and I didn't ever think we'd even get 100. All right, so I'm up to 400 and something now. So I really appreciate everybody participating and liking. I guess like and subscribe and do whatever you're supposed to do on YouTube, which whatever that is, I don't know. All right, guys. See ya. Bye.